Hi, welcome back. In this lecture, we will present how the B method provides support to an important programming construct, loops. By providing support to loops, the B method guarantees that loops terminate and work as they are expected to do. This technique uses two things. First, an invariant to guarantee the correctness of the final state, and second, a variant to guarantee termination. Loops can only be used in implementations. Our overall structure of loops is the following. While the guard E is true, do the command S, respecting the invariant I and the variant V. As an example, let us develop a program that initializes an array of size 10. This can be abstractly specified as the following command: a variable tab receiving a random element of the set containing all the total functions from the set of numbers ranging from 0 to 9 to the finite set of natural numbers. Let us now implement this as a loop that assigns 1 to all elements of the array. First, we must correctly initialize control variables and declare the guard and the body of the loop. Here, in this command, we first declare a variable II and we use it in the following block. We first initialize II with 0 and then we have the loop. The loop, while II is less or equal 9, we do the following. We assign to the position II of tab the value 1 and then we increment II by 1. With this specification, however, we cannot yet guarantee the correctness of the loop. This correctness is related with a requirement, the postcondition of the loop. In our case, we have the postcondition of the loop is the following predicate. For all xx, if xx belongs to the set ranging from 0 to 9, then tab at position xx equals 1. The loop execution will have an initial state and may have many intermediate states until we reach the final state of the loop that satisfies this postcondition. Any special condition will be satisfied at every of these states, the invariant. This means the invariant is true at the very beginning of the loop and at the end of every iteration of the loop. When the loop terminates, together, the invariant and the negation of the guard that caused the loop termination will guarantee the postcondition. In summary then, to guarantee the correctness of the loop, we must find its invariant and ensure three conditions. First, that the commands before the loop establish the loop invariant. Second, that provided that the invariant and the loop guards are true, the body of the loop establishes the loop invariant. And finally, that provided that the invariant is true and that the loop guard is false, we can guarantee the postcondition of the loop. In our example, we have that in the initial state, II equals 0, and the postcondition of the loop is the following predicate. For all xx, if xx belongs to the set ranging from 0 to 9, then tab at position xx equals 1. The invariant construction is usually an iterative process by adding predicates that appears in unproved or unprovable proof obligations. In our example, the invariant is a predicate on II and tab that is true in the initial state, preserved by the body of the loop, and also that establish that the postcondition is true when the guard is false, that is, when II equals 10. Let us propose the following invariant. Tab belongs to the set of functions from numbers ranging from 0 to 9 to natural numbers, and II belongs to the set of containing numbers ranging from 0 to 10, and that for all xx, if xx belongs to the set of numbers ranging from 0 to II minus 1, then tab at position xx equals 1. The first part of the predicate that talks about the tab belonging to the set of functions from numbers ranging from 0 to 9 to natural numbers is used to make the proofs easier. And the second part of the predicate that says that II belongs to the set of numbers ranging from 0 to 10 is needed to guarantee the correctness of the variant, as we will see later in this lecture. So first, in the initial state, II, as we said, equals 0. So the predicate, the invariant, in the invariant we replace II by 0, and we get the predicate tab belonging to the set of functions from numbers ranging from 0 to 9 to the natural numbers, and that 0 belongs to the set of numbers ranging from 0 to 10, which is trivially true, that for all xx, if xx belongs to the empty set, which is exactly what we get if we get the set of numbers ranging from 0 to 0 minus 1, from 0 to minus 1, that gives us the empty set, then tab equals 1. So we have that tab is the set of total functions, which is true because it's the type of that variable. For the body of the loop, if we carefully analyze its behavior, we will confirm that indeed, after every iteration, the array elements at indexes ranging from 0 to II minus 1 will have the value 1. Finally, in the final state, II equals 10. So if we replace II now by 10, we have to prove that 10 belongs to the set containing numbers ranging from 0 to 10, which is trivially true, and that for all xx, if xx belongs to the set of numbers ranging from 0 to 10 minus 1, which is 9, then we have that tab at xx equals 1. And that implies exactly our post condition. In our loop now, we add the invariant that we have just proposed. So we add the invariant saying that tab belongs to the set of total functions from numbers ranging from 0 to 9, to the finite set of natural numbers, and II belongs to the set of numbers ranging from 0 to 10, and that for all xx, if xx belongs to the set of numbers ranging from 0 to II minus 1, then the tab at position xx equals 1. The invariant guarantees that when the loop terminates, we reach a final state that satisfies the post condition of the loop. It, however, does not guarantee termination. For that, we must ensure that the loop is moving towards a final state at each step. In the B method, we use the variant, a natural expression that must be decreased every time we execute the body of the loop. By enforcing the variant to be a natural expression and that it is decreased every time we execute the loop, we guarantee a finite time of iterations. The initial value of the variant is the maximum number of iterations of the loop. In summary, to guarantee the loop termination, we must find a variant and ensure two conditions. First, the loop invariant and its guard guarantee that the variant is a natural expression. Second, provided that the invariant and the loop guard are true, the body of the loop decreases the variant. Let us propose, in our example, the variant to be 10 minus II. Analyzing the code, we can see that the body of the loop always increases the value of II. Hence, it decreases the value of the expression 10 minus II. Furthermore, the value of 10 minus II is at least 0, and hence it's always a natural number, since its values ranges from 10 when II is 0 to 0 when II is 10. So now, in our loop, we also add the variant, and the variant is defined to be the expression 10 minus II. Just as a hint, it's a good idea to keep loops alone in an operation. If two loops are needed or mixed with other instructions, then decompose and have one loop per operation. As a second example, let us develop a loop that implements the Russian multiplication. To multiply two numbers, AA and BB, this algorithm uses a table with two columns, say XX and YY, with AA and BB in the first line of the table. At each iteration, we divide the first column by 2, rounding down, and multiply the second column by 2 and include the results as a new line. We repeat this until we get 0 in the first column. The result is the sum of the elements in the second column whose corresponding element in the first column is odd. It's assigned to a variable called total. For example, say we want to multiply 57 by 43. We have the following calculation. We start with 57, the first column, and 43 in the second column. Then we divide by 2. So we get 28, the first column. We multiply by 2 the second column, getting 86. And then we keep doing this, getting 14 and 172, 7 and 344, 3 and 688, 1 and 1,376, and finally 0 and 2,752. So next we remove the lines in which II is odd, and finally we get the remaining lines of II. So we get 43, 344, 688, 1,376, and we sum these numbers, getting the final result 2,451. Let us now implement this loop. First, we must correctly initialize the variables and declare the guard and the body of this loop. So we declare the variable xx and yy in the following block. We initialize xx with AA, yy with bb, and total with 0. And while xx is different from 0, we do the following. We declare a variable called rest and assign to it the value of xx mod 2. So if rest is 1, then we have an odd number. So we add to total the value of yy. Finally, in the loop, we divide xx by 2 and we multiply yy by 2. At the end of this loop, we have that the post conditions the following predicate. Total equals AA times BB. In our example, we have that in the initial state, xx equals AA, yy equals BB, and total equals 0. And our post condition is total equals AA times BB. The invariant is a predicate on xx, yy, and total that satisfies 3 conditions. It's true in the initial state, it is preserved by the body of the loop, and it also establishes the post condition when the guard is false, that is when xx equals 0. Let us propose the invariant to be the predicate total plus xx times yy equals AA times bb. The initial state, when xx equals AA and yy equals bb and total equals 0, we have that the invariant becomes the expression 0 plus AA times bb equals AA times bb, which gives us the predicate AA times bb equals AA times bb, which is trivially true. For the body of the loop, we can look at this table. Notice each time we divide xx by 2 and we multiply yy by 2, we keep the expression total plus xx times yy equals AA times bb true. For example, at the very first time we run through the body of the loop and we get 28 and 86, we have, for example, that 43 plus 14 times 172 equals 2,451. And this is actually true at every time we run through the body of the loop. You can actually pause the video now and check that all these expressions are actually true. Finally, in the final state, when xx equals 0, we have that the invariant becomes the expression, the predicate total plus 0 times yy equals AA times bb, which gives us the predicate total equals AA times bb, which is our post condition, which is the post condition of the loop. So now we add to our loop the invariant saying that xx belongs to natural, which is used to guarantee that the variant that we'll talk about next is always a natural number, and total plus xx times yy equals AA times bb. Next, let us propose the variant to be xx. As we can see here, the body of the loop always decreases the value of xx because it's always dividing xx by 2. And this value is at least 0, and hence it's always a natural number since its value ranges from AA to 0. So finally now we can add to the loop the variant xx. So you can see here why we have added xx belongs to natural in the invariant, because by having that in the invariant, we guarantee that the variant is a natural expression. Let us now see this example in Atelier B. Let's see the abstract specification, the implementation, and then generate code and run this code. The abstract specification of our Russian multiplication is very simple. It is a machine multi-Russian that has one operation called mult and receives two numbers, AA and BB, both being natural numbers, but it's very important that the multiplication does not overflow the finite set of natural numbers. So we have to guarantee that the multiplication still belongs to the finite set of natural numbers. And then we have that the total receives the multiplication, the value of the multiplication of AA by BB. And we assign that to total and give this as output. The concrete specification is exactly the loop that we have seen. So we have the same operation, mult, AA, and receiving AA and BB, and we have the loop that we have just seen. So we declare two variables, xx and yy. We initialize xx with AA, yy with BB, total with 0. And while xx is different from 0, we do the following. We do the body of the loop. We declare rest, and we assign to rest the value of xx mod 2. And it's very important to notice that we cannot use this expression here in the condition of the if then else, of the if block. So we have to really declare a variable here and assign to it the value of this expression xx mod 2. And then if the rest is equal to 1, then we assign to total the sum of total and yy. Finally, we divide xx by 2, and then we multiply yy by 2, and we have the loop invariant here, as we have already explained it, and the variant loop here. So now we can actually generate code. So we right-click on the implementation, and we select the code generator. As you can see here in the message, the translation was successful, and we go into the project folder, which in my case here is at the documents folder, and can here in the lang folder of the project we have the generated C code. So our C code is actually quite simple, as you can see here. We have the calculation of the concrete constants, which you don't have in this case. We have the initialization that simply does nothing, and here is our operation. So it receives two numbers, AA and BB, and assigns to total the value of the multiplication using exactly the algorithm that we have seen here. So we now can declare a main file in which you choose what to do actually. So here I have chosen to AA to be 30, BB to be 7, and we have the total here, and I invoke the operation mult of the machine multi-Russian, given AA and BB as input arguments and total as an output argument. So I give the address of total as argument. And then we print the result. Now, if I simply compile and run this code, we can see here that actually we have actually executed, and the result is exactly what we expected. 30 times 7 equals 210. And that completes our example of the Russian multiplication. To conclude this lecture, let us present a simple example of a machine that has one array as its only state component, and an operation that indicates if a given number is a member of the array. The implementation of our example has two loops. In the initialization, we develop a loop that sets all elements of the array of size n to the value of its index. Finally, we also use a loop to try to find a given number in the array. Let's see. The machine array search is relatively simple. It has a constant called max, which represents the maximal index of the array, and it has the array as a variable, so it declares a total function from the set ranging from 0 to max to the finite set of natural numbers. We initialize every element of this array to be exactly the value of its index. So we declare AA, we assign to AA the function, so here we use the lambda expression, saying that for every II, where II ranges from 0 to max, we map that II to itself. So we map the value II to II. So this gives us the function that maps 0 to 0, 1 to 1, 2 to 2, up to max mapped to max. We have three operations in this machine. You have the get operation that receives a valid index, so XX must belong to the domain of the array. So it's that set containing numbers from 0 to max. And we assign to the output variable EE the value of the array at position XX. To add an element, II, at position XX to the position II of the array, we receive also a valid index II and the value that we want to add to the array. And we simply say that the array at position II receives the given value XX. Finally, we have the contains operation that returns true, the value true, if the element, the given natural number XX belongs to that array. So we simply return the Boolean value, so we use here a function that gets the result of this predicate, in which we check if XX belongs to the range of AA, and it turns it into Boolean value, so it returns this value at the output variable BB. To implement that array, we have an implementation, let's call it array search I, that refines array search, and also contains a variable that this time concrete variable, so we declare the concrete variables to be AA, and since we are using the same name, we have that AA equals the abstract AA, so it's also a total function from 0, from the set that contains elements, numbers ranging from 0 to max to the natural numbers. And we have to value the constant max. So let's say we say that max equals 9. So now we have an array of size 10 because our indexes ranging from 0 to 9. And we have two loops here. First, in the initialization. So to initialize all elements to be exactly the value of the index, we use this loop here. So we have a control variable called II. We initialize it with 0, and while this variable is less or equal than max, we do exactly these two commands. We assign to the array at position II the value II, and we increment II. And as we can see here, every time we go through the body of this loop, and before reaching the loop, we have that for all JJ, where JJ belongs to the set containing numbers ranging from 0 to II minus 1, we have that the array at position JJ equals JJ. So as you can see here, every time you go through the body of the loop, we have an II, and we have already set all numbers before that index II to be the correct value we want. And we must also ensure that II is less or equal to max plus 1. And this guarantees that our variant here is a natural expression. So we have that max plus 1 minus II is always decreasing. We must add this plus 1 because at the final time we go through the body of the loop, we have that II is greater than max. That's what makes the loop stops. So we have to put +1 here to guarantee that we have a natural expression here. Finally, we have the get operation, which is exactly the same. We just remove the precondition. Also, to the add operation, which is exactly the same. We just have removed the precondition. And finally, we have the contains operation, which is implemented as a loop also. So we have the answer RR, and we have the control variable II. So the RR variable is initialized with false, and the II is initialized with 0. And while II is less or equal than max, we have that RR and RR is equal to false. So while we have not yet found the element, and while we have not yet going through the whole loop, we execute the body of the loop. So we get the element at position II. So we declare a variable EE, and we assign to that variable the element at position II. And that again, we must do that because we cannot access the element of the array. We cannot use this expression here at position at the condition of the if block. And we also increment here. We have already incremented the I here. And finally, we check if EE is equal to the value we have received in the operation XX. If that's true, we assign true to the variable RR. And in the invariant of this loop, we can see that actually the RR, the variable RR is true if and only if we have already found the given value, the value of XX in the part of the array we have already gone through. So if XX belongs to the range of this part of the array, so that's the array restricted to the index 0 to II minus 1, then we have that our answer is true. And we also, as we did here with the initialization, we have to guarantee that II is less or equal to max plus 1. And our variant is exactly the same as we had in the initialization. Finally, after the loop, I have just assigned the value of the variable RR, that's our answer, to the output variable BB. So that's simply to give the output of the loop. Now we can generate code for this implementation, and here, so now we have the array search. So we have here the code in which we have the initialization as we expect with the loop, the corresponding loop. We have the operations get, the operations add, and the loop of the operation that initializes the variable RR and II, and while II is less or equal the constant max of the machine array search, and RR equals false, we do what we exactly did in the implementation machine. So we have a variable EE that receives the value of the array AA at position II, and we increment II, and we check if EE equals the value we received XX. In that case, we assign true to R, and finally we assign, after the loop, we assign to BB the value of RR. So I have created here a main. I have a simple function here that just prints the array, okay? And then what I've done is I have initialized the machine, and so at this point we know that every element of the array has the value that is equal to the index, to its index, and we check if 0 is there. So we have a boolean that's given to the operation contains of the function contains of the array search, and we print that answer. Then we check if 9 is there, we check if 5 is there, and we also check if stands there. So the expect answers are true, 1 in the case of C1, again 1 here, again 1 here, and 0 for this. And finally we add at position 9 the value 100, and we ask if 9 is the array, and the expected answer is false, of course. It is very important to notice that in this example, just like in the other examples, we have manually written the C code in the main file. Our code does not verify the preconditions of the machine array search. Therefore, integration tests between our manually written code and the automatically generated code is needed. Another approach is to define another machine, say robust array search, that imports array search and turns it into a robust machine that returns error messages in cases in which the preconditions is not respected. So let's see here. Let's compile and run this code. So as you can see here, we have the right, the expected answers. So after the initialization, we have the array ranging from 0 to 9 at position 0 to 9. And 0 was there, 9 was there, 5 was there, and 10 was not there. And finally, that we replaced the element of the index 9 to 100, and we asked if 9 is there, and the answer was expected no. So that actually completes our example of the array search. And that's all for this lecture. I hope you enjoyed it. And remember, FOMO is fun.